Today's lesson is on describing a quantitative variable. Moneyball is a movie about the Oakland A's baseball team and their 2002 season. When the movie came out, it was a big hit. At the box office, it grossed $110 million. However, the wide popularity of a movie about the Oakland A's 2002 season is a bit of a surprise because in the 2002 Major League Baseball season, it was the Yankees, not the A's, that scored the most runs. It was the Braves, not the A's, that had the largest division lead at the end of the season. And it was the Angels, not the A's, that won the championship. So that brings us to today's key question. Why would anyone make or even watch a movie about the Oakland A's? With that in mind, let's move into our guided notes. We're going to discuss 4 topics today, starting with dot plots. All right, there's some good scenes in the movie Moneyball. I can't play it on here right now, but if you're curious and want to see it, go check this scene out or watch the whole movie. It's great. But basically, what that clip talks about is in professional baseball, there's rich teams and there are poor teams. This table that you see there shows all the teams' payrolls from the 2002 season. Payroll for a team is the total amount of money they pay their players. The payroll measured in dollars is a quantitative or numerical value. The New York Yankees had the highest payroll at $126 million. This means that they could easily afford to recruit star players to their team. Meanwhile, the A's had the third lowest payroll at $40 million. With a lower payroll, it's more difficult to attract star talent to your team. We can take this quantitative data and construct a dot plot. The dots show the payrolls of different teams, and teams with highly similar payrolls are stacked on top of one another. The New York Yankees are represented by this dot at $126 million. And the Oakland A's and Minnesota Twins are represented by these 2 dots, which are stacked since both of their payrolls were about $40 million. One advantage to using a dot plot is that we get to see every data value as its own dot, laid out on the full scale of the data. This is especially useful for smaller data sets. A couple of disadvantages is that we can't see each point's exact value. If a dot falls between tick marks on our scale, we have to slightly eyeball its exact value on the x-axis. Another disadvantage is that because every data value gets its own point, dot plots can be a bit overwhelming to look at for very large data sets and can make patterns difficult to see. So that first disadvantage brings up a question. How can we visualize every data point's exact value? That brings us to our next type of quantitative variable graphs, stem and leaf plots. To make a stem and leaf plot, we first have to figure out how we'd like to group our data. We see that we have 2 teams with payrolls in the $30 million range. We have 7 teams with the payrolls in the $40 million range, 5 teams in the $50 million range, and so on and so forth. So what we can do is put the teams into groups of tens of millions of dollars, starting with from 30 million to 40 million, all the way up to 120 million. We call these groupings the stems. Think of them like the stems on a plant. From the stems, we will extend the leaves, or the individual values of each team. For example, the Tampa Bay Rays had the lowest payroll at $34 million. We can represent this payroll using the $30 million stem and giving the Rays a leaf of 4. Together, this stem of 30 and leaf of 4 represents $34 million, or the Rays payroll. Because the Montreal Expos had a payroll of $39 million, we can represent them with a leaf of 9 in the stem of 30. Because the A's had a $40 million payroll, they moved to the $40 million stem and have a leaf of 0. Same thing with the Twins. And we proceed through the rest until all the data is represented in our plot. Note that if asked to make one of these plots in the AP exam, you should make sure to include both a title and a key. The key advantage of a stem and leaf plot is you get to see the exact values of every data point in ways that might be a bit more difficult in a plot or in other kind of plots. However, a disadvantage is, again, that they can be overwhelming to look at for larger data sets. So this raises a question: what is a good quantitative data visual for larger sets? That brings us to the final graph type we'll be discussing today, histograms. Let's see if we can summarize this data more compactly. To do so, we're going to organize the data values into intervals called bins. Note that it's fairly standard for these intervals to include the lower bound, hence the less than or equal to signs. And it's fairly standard for these intervals to exclude the upper bounds, hence the less than signs without the equal to notation. We see that there are 2 teams in our data set that fit into the first bin. Note that the A's with the $40 million payroll don't go into this bin since that upper bound is excluded. Instead, they go into the next bin where there are 12 teams. And we can fill in the rest for a total of all 30 teams captured from our data set. And it's worth noting that only 1 team had a payroll in the highest interval, the New York Yankees. Using our table, we can now construct a histogram. We're going to use the x-axis to represent the variable we're measuring, the team payrolls, and we're going to use the y-axis to represent the frequency of different payroll values. When we do that, this is what we get, a visualization of these bins known as a histogram. You might notice that it's somewhat similar to a bar graph. However, unlike a bar graph, there are no spaces between the bars, indicating that we're visualizing a quantitative variable here rather than a variable with distinct categories. The best way to read a histogram is to look at the bar heights. For example, we see that the 80 to almost 100 million bin has a height of 4. This means that 4 teams have a payroll between 80 and almost $100 million. It's important to note that the height of the bar doesn't indicate that these teams have higher or lower payrolls. In fact, the highest payroll team, the Yankees, are represented by the bar with the lowest height. The height of the bar merely represents the number of data values or frequency of data values in a certain interval or bin. In this case, only one team, the Yankees, fit in this very high bin. In addition to looking at the frequencies of data values in these bins, we can also look at the relative frequencies or proportions. For example, we can see that there are 2 teams with payrolls between $20 and almost $40 million out of a total of 30 teams. We can represent this relative frequency by dividing 2 by the total of 30, which yields a proportion of 0.067, or 6.7%. So 6.7% of teams have a payroll between $20 and almost $40 million. Similarly, there are 12 teams in the next bin. Out of 30 total teams, this yields a proportion of 0.4, so 40% of teams have payrolls between $40 million and almost $60 million. We can do the same for the rest. Note that the relative frequencies, the total should be 100% or all the teams. We can take these relative frequencies and construct a relative frequency histogram. It basically looks the same as the raw frequency histogram earlier, but now the y-axis represents the percent or relative frequency of each bin. So the bar heights tell you the percent of the data set contained within a certain bin. The key advantage of histograms is they're great for summarizing large data sets, as the bins help to group the data, making the patterns easier to see. However, the largest disadvantage is that you can't see individual data values. Instead, you can only see an interval that contains the exact values. Finally, let's talk about describing a quantitative data set. And this may come as a surprise to you, but in statistics class, we ask you to cuss. Yes, that's right, we ask you to cuss in class. And all we ask that you make sure to cuss is with context. What does that mean? Well, it means you'll sometimes be asked to describe center, unusual features, shape, or spread of a quantitative distribution, or CUS for short. And when you're asked to describe these features, you always want to make sure to include context. For example, here's the histogram of the team payrolls. So maybe asked to describe the center of a graph like this. The central value of this distribution, or the middling value, appears to be between 60 and almost $80 million. Note this is a visual estimate of the central values of the distribution. In a later lesson, we'll learn how to calculate more specific measures of center, such as means and medians. So that's what we'd write in our response. The distribution of team payrolls is centered between 60 million and almost $80 million. Note that in my response, I made sure to mention the context of the variable being measured, team payrolls. Next, you may be asked whether there are any unusual features. To see what unusual features could look like, we imagine what the distribution actually looks like instead. So one unusual feature would be the gap from 80 to almost $120 million. The other unusual feature would be that this highest paying team is a potential outlier, and its payroll is unusually high compared to the rest of the data set. However, our graph actually looked like this. As you can see, there's no gap. And the highest paying team is no longer paying an unusually high amount compared to the rest of the data, so it's likely not an outlier. So we can respond that there do not appear to be any gaps or outliers, and therefore no unusual features are visible. You may be asked about the shape of the distribution like this. Let's discuss what we mean by shape. When describing shape, you can comment on the number of modes or peaks. Distribution has 0 prominent peaks or modes, we say it's approximately uniform, meaning that the frequencies are uniform or similar across all values. If it has 1 clear peak or mode, we say it's unimodal. Finally, a bimodal graph has 2 peaks or modes. Another important aspect of shape is described as symmetry or skew. If a distribution has a tail on the left, it's called left skew or negative skew. A tail on the right indicates a right skew. And a distribution in which each side is roughly the mirror image of the other is considered roughly symmetric. Now, you may have noticed the word skew appears in the name of this organization we use, Skew the Script. This is no accident. As educators, we notice that when we use the usual script of teaching math and statistics with irrelevant examples, such as Bob having 85 watermelons, or calculating The mean lifetime of batteries, student scores look like this, a right skew. Many low scores on the left and only a few high scores on the right. However, when we went off script and used math and statistics to explore genuinely relevant concepts, students engaged much better and became left skew. Very few low scores on the left and high scores on the right. So we can draw a line above the frequencies on our graph to get a better sense of its shape. And the line makes it clear that the distribution of team payrolls is right skew with a tail on the right. It's also unimodal with just one prominent peak. Finally, may be asked to describe the spread of a distribution. We see that these values vary from low end of 20 to almost $40 million, up to the high end of 120 to almost $140 million. We'd say in our response that team payrolls vary between those individuals. Now that we've done all this work, let's get back to our key question. Why would anyone make or watch a movie about the Oakland A's? As we saw before, the A's had a much lower team payroll than wealthier teams such as the Yankees. To make up for that, they had to develop a strategy. And that strategy could be explained in the movie. Basically, they're trying to find undervalued players that can fit what they need. They're one of the first teams to use advanced statistics to identify undervalued players, in other words, effective players that they could afford. The result was even though the distribution of team payrolls looked like this, the distribution of wins looked like this. The Yankees, as you may expect, won an impressive 103 games. However, the A's did almost as well, won 103 games. Put this in perspective, this means that with their payroll, the Yankees spent about $1.2 million per win. The A's were $0.4 million per win. So that brings us to our discussion question. Major League Baseball has a luxury tax. Rich teams have to pay extra money to be able to help fund the poor teams. However, the poor teams say that the tax isn't big enough to make much of a difference. Imagine that the league enacted a harsher and bigger tax in the 2002 season, the same season from the movie and from the data we collected. And the money spent above $100 million on payroll is taxed at 90% rate. So 90% of that money is taken by the league and given to the poorer teams. This leads us to two discussion questions. How would this change the distribution of team payrolls? Comment on center, shape, and spread. And in your opinion, would this new system be better for the sport? Why or why not? Take a moment, jot down initial thoughts, and we'll discuss them further in class. That's it for today. See you next time.